project on hierarchical imitation and reinforcement learning. Our group member includes Huang Yongxiang and Chen Guang. One problem in reinforcement learning is that there are some tasks that require a long horizon and there are only sparse reward. And these papers trying to tackle this problem by using a hierarchical structure. Normally, to solve the sparse reward problem, people can use imitation learning to provide the agent with supervised label, indicate for the correct steps. But the labeling cost could be significantly large for a large action space. So to improve the efficiency for labeling, this paper proposed to use the imitation learning for a high-level agent learning and then apply reinforcement learning in the low level to execute the correct macro action predicted by the higher level agent. There are two tasks in this paper. The first task is about the maze navigation. The agent have to navigate from the starting position to the destination marked as the yellow grid in this image. And it has to avoid hitting the lava, which is the red block in the image. And the second task is an entire game called Montezuma's Revenge. In this game, the agent has to at first get a kid in this position and then exit the door through this ladder. By using the typical deep Q-learning network, the agent can only achieve 0 reward, as reported in the DQM paper. So the proposed method use this framework. There is a method controller that receives the current state, which consists of the 4 previous frames of the game, and it predicts a sub-goal for it to take. And for each sub-goal, there is a controller to learn to achieve each sub-goal. The intuition is very simple. For human, if we want to navigate from one place at home to the other, we may say you can go through the left of the corridor and then go left at the end of the corridor. Then you can go to the restroom. So for the maze navigation task, this is similar. The agent can be told to at first escape the first 4x4 grid room in the south and then head to the east in the second room, and so on. So we implement this framework by using TensorFlow and Keras. And here are the experimental results. We will first show how the agent acts on these two tasks. We will first show the task performance, the model performance on the first task in real time. So here we applying the reproduce model on the maze navigation task. We can see that for each generating map, the agent can successfully find its way to the destination while avoiding each lava. And now we can see the overall performance of our improvement and the original performance of the proposed method. The original proposed method reached a success rate about 0.5 when it converges, while our method converged to about 0.99. We apply two strategies to improve the performance. First of all, as the original network architecture for imitation learning ignore the boundary information of the map, we use appropriate padding to utilize the boundary information. Because the boundary information includes the lava that the agent has to avoid. So by better utilizing this information, the agent should be able to better navigate to the destination. And the second strategy is to increase the representation capability of the network. The original imitation network only apply 4 convolutional layers and 1 fully connected layer, which is quite shallow. We increase it by increasing 2 convolutional layers and adding dropout regularization and L2 non-regularization to avoid overfitting. By using these 2 strategies, we achieve a significant improvement on the success rate. And on the second task, the Montezuma's Revenge, the method controller is implemented by imitation learning, and the primitive action controller is implemented by reinforcement learning based on double DQN with pre-authorized experience replying. Now we first look at the demo of this on this task. We will first show how the agent acts based on the trade model of the original method. So here the agent achieves subgoal 0, and when it's trying to get a key, it jumps into the skull and lead to a death and game over. Just because we add a variation here in the original paper, the skull always appear at the same position, and this never changes. The overall method lacks some adaptation to the new environment actually. So to avoid this problem, we randomly wait for the skull to move to another position before the agent take any action. So now let's see how our improved agent act on this task. So you can now see the agent can fluently pass the skull and avoid jump into the skull. And this is the second trial. It still successfully passed the skull and then get a key and then exit from the first room. Just now we can see the agent wait here until the skull to move another position. Okay. Here we visually verify the improvement of our proposed strategy on the second task. And on the quantity comparison, we can see from this table, as compared to the original result, we can see that for subgoal 2, corresponding to getting the key, the learning progress is more fluctuating than the original results, because the horizon of the subtask is much longer than the first one, so as the last subgoal. We also investigate how the learning strategy or optimization method effect on the final performance of the hierarchical imitation and learning and reinforcement learning method. And compared to supervised learning, reinforcement learning using DQN is much more sensitive to the optimization method, since the input to the reinforcement learning and the target Q value function to change is non-static during training. So in our experiment, we can see that only one test running right can successfully train out all the subgoals here, and the stochastic gradient descent with momentum optimizer cannot train even one subgoal in this task of the Montezuma's revenge. And we also test the batch size. The batch size have a comparatively smaller effect on the final performance compared to the learning rate. So to conclude, we have reproduced the results on the two tasks that corresponding to the experiments part of the paper, and we also propose to improve the performance on these two tasks by taking two valid strategies in the first task and another at a strategy to increase the adaptation of the agent on new environment on the second task. Thank you, that's all.